Okay, so I'm being lazy today. So what we're supposed, well, we want to do in like what's integer programming or integer linear programming? Well, you don't know which answer. There are many possible answers. Yeah, it's a technique, right? So it's an operational research. Students hate it. Most of them do. Like you guys don't because you chose it, or if you're in financial, then you hate it. But if you're not in financial, then perhaps you like it, or you like Philip or something. So you chose it. Okay? But students hate it because it's not like you're not building a theory or something. It's more like a collection of techniques, like a toolbox. Okay? And there comes this problem that, I don't know, you want to solve using, yeah, no. You don't need to read it now, I'm talking about something else. Yeah, so for this problem, you take a network model and you do a maximum flow or something. For that problem, you take a linear programming model. And I think there's so why don't students like decision maths in the first year? Well, you know that, but I'm just guessing. I'm guessing it is because in most other things, you get question, okay, and then you're taught the method, and you just take it, okay, and this is I don't know, this is Gaussian elimination, and you know what to do, and you just go and you and then it's done. And to some extent, that's the case with the simplex method. So you get easy problem, and you put it into the tableau, and you go pivot, and you end up. But many of those questions are more like, you've got this situation, and then produce a mathematical model. And that's hard, because you have to think. When you get a system of linear equations, and you're told to do the Gaussian elimination, and you don't have to think, you just do. So there is this bit. And another thing why I don't think students like it is because it's not building on top of these things like you do when you're doing analysis with Killian, for example. And it starts with no sequences, and then from sequences you go to functions, and then limits of functions, and then derivatives, and I don't know, and it's kind of builds like a theory. But in decision maths, this is a little toolkit that solves this kind of problems, and then we've got another one here and another one there, and you don't really know which one to use, and so it's confusing. Why am I saying this? Because yeah, so I'm procrastinating today. So where has it gone? Right. So what? Okay, this doesn't work. You broke my iPad. I'm looking at the projector, not at you. Okay, so what we've been doing for the past 2 or 3 weeks, perhaps, was you get a linear programming problem, and then there is an algorithm to solve it, and we've learned about this algorithm because it's important to know this algorithm. Because it's, yeah. But what is perhaps more useful, and what we're going to do now for a couple of weeks, is looking at a problem that's described in a silly example like this one, okay? And what you want to get is the actual formulation. So the decision variables is this, the objective is this, the constraints are like this, okay? That's the point. It's always the same, I keep saying it, again and again and again. When you ask for an integer linear programming formulation, you will always have to give decision variables, the objective, and the constraints. Okay. So in this case, I'm assuming that everybody has read the question. Okay, what are the decision variables? Or what decisions does the burglar need to make there? Well, that are related to them. Okay, it doesn't ask a question, does it? Well, let's which items? Okay, you can call me sexist, and I'm writing he and not he or she or they or something. But it's a burglar. I mean, it's obvious. It must be made. So, what are the decisions? What is the what are they trying to do, or what is he trying to do? Exactly. So, how would you put it into integer numbers? Yes. Do you want to say anything? Okay. Remember the trick we had. We've had an example like this. Okay, we have had two examples. One of them was like this. The first one was the cargo ship, and the other one was management. So none of them was like this. But the cargo ship was a bit like this, because in the cargo ship we had some containers. And for each of them, we were trying to decide how many of them to take. So that's exactly like that. For each of the 8 items, you want to decide how many of them to take. It's going to be 0 or 1. It can't be anything more, because each item is there only in one unique example. But other than that, it's the same. So you take a variable for each of these items, and you want to decide. And sorry, what the variable is going to mean is the number of items I that you want to take. Okay, so they will be x1, x2, x8. Now, each. So we should give an interpretation of what they mean. So each xi is 1 if the burglar takes item I, and it's 0 if not. It's extremely common in integer programming formulations that you have these what's called binary variables. I think I've said it before. Binary because they can take 2 different values, 0 and 1, and they signify that whether something happens or not. Okay? That's it's a ubiquitous thing in integer programming. Okay? So now, what is the objective? Correct. Okay, what's the objective? Maximize PI. But PI you can't maximize because PI is given. But maximize sounds good. He wants to maximize the total value. Yes? How'd you know? So yes. It usually says this. The sum of all PI times XI. Okay, you said XI times PI, but multiplication is commutative. I goes from 1 to 8. Yeah, why? Okay, who wants this explained? No one. Okay, so we can move on. You got off the hook. Why? Yes, it is. Whoever.
Because each item has a value.
Yeah, okay. So you want to maximize the total value taken? Why is the total value taken given by this formula? Well, okay, x1 is 1, that means you're taking the thing, then you're counting its value into the sum, and if xi is 0, that means you're not taking the thing, you're counting 0 into the sum. So when you add them all together, it gives you the sum of the values, it's called the values of all the items that you decided to take. So that's one. It needs much more explanation. Am I going too slowly? Okay. Constraints. Obviously, you can't exceed the total weight, so you sum the total weight. Can't be more than, what is it, W? And, of course, they're all supposed to be binary. Next problem. Am I going too fast? No. Any questions? Same trick as before. The sum gives you the total weight of all the items you're taking. Can't be more than what you can carry. And then, akin to non-negativity that you're used to from linear programming, you want to specify that these variables only take on the values that you want. Okay, next question is, it's a bit of a silly problem, really. Sorry. Okay. What? No, in fact, it's really stupid. So.
Yeah,
What? Yes, voda is water in Russian. I don't know what happened to telecom. No, but the question. Okay, so I is the set of all the telecoms AOH. The fixed charge, I'll call it FI, and the cost per minute, I'll call it CI. Okay. So you see there are two things. Decide which company should I subscribe to. No one's watching. Which companies should I subscribe to? And the other question is how many minutes should I do with each company? Okay, it's a bit of a silly. I mean, it shows the principle of questions like this, but perhaps it's not. It's a bit of an overkill. Okay, but it's a simple example. I mean, you wouldn't really want to do it with integer programming, but it's an example of a certain thing, so that's why it's here. Right. It'll be an example of what's called MIP. Mixed integer programming. Okay, we won't be doing much theory of MIP because there's no time. But mixed comes from the fact that there will be both integer and non-integer variables. Okay, so it has some variables. Some decision variables are integer, others are real. That's not on the exam to explain what MIP means. So, but that's what it is. That's what it is. Okay, so what are the decision variables? No. I say it wasn't important. Are integer and others are real. So what are the integer decision variables in this case? Pardon? No, these are just letters for the telecoms. No, fixed charge is part of the data. Whether you subscribe or not, yes, that's a good decision. What do you want to call it? SI. So for each of the three telecoms, I have one SI, which is one if I subscribe to that particular company, and it's 0 otherwise. Okay, any real variables? Sorry?
FI and CI.
Oh, these are, well, decision variables. FI are not, and CI are not decision variables because FI and CI come from the outside world. Those are not the things that we're deciding. Those are the parameters or data, or whatever you want to call it, but not decision variables. But the other question on the problem was how many minutes should I spend with each of the 3 telecoms? What do you want to call it? XI. Did you say X? No, you can call it XI. Did you say XI?
I said
So again, for each telecom, I have M, and this is the number of minutes. With that particular telecom, what is the objective? Minimize cost. Lip is looking suspiciously. Maybe that's not because of me. Probably is. Okay, so what is the total cost? Like this? Or like this? So where's the SI? Just because I left space there, right? Okay, any better reason? That's quite right, yeah. So you just want to pay the fixed charge for the ones that you select to take a subscription with, rather than with everybody. And that gives it to you. So, okay, that's good. Constraints. Okay, so some constraints are easy. For example, the constraint that you want to, what is it, 200 minutes? 200 minutes. So when you add all the minutes, you want to get 200. Okay, that's simple. Also, what else is simple? Another thing is that's simple is that you want each of the SIs to be 0, 1, and you want all the minutes to be non-negative. They don't have to be integer. You could do like 31 minutes and 17 seconds with one of them. Okay, there's a constraint missing, as you can tell by the space that I've left. And so what could go wrong with this formulation? Okay, I can tell you the optimal solution. I know the optimal solution of this. All the SIs will be 0, so I'm not taking any subscription, and I'm spending 200 minutes with O3 because that's the cheapest per minute. That's the solution we're in this formulation. Because there's nothing preventing me from setting all the SIs to 0 and still making phone calls. Okay? So we need to put in a constraint that stops me doing that. So we need a constraint which makes sure that we're not taking any minutes with a certain telecom if we're not subscribed to. And that's probably, I mean, if I gave you a lot of time, you might come up with it, you might not. Oh no, not again. No. Good. You might come up with it, but maybe not. The first time you see it, it might seem a bit obscure. So what you want is one of these constraints for each of the operators. And you want that the number of minutes should be no more than 200 SI. Or 2000 if you want. Doesn't matter what. The 200 should be large enough to not prevent you from doing anything. SI is 1. So what this constraint does is, if SI is 1, it's not supposed to do anything. Because if SI is 1, you can do what you want with that. What it's supposed to do is, if SI is 0, then it makes y equals yes, 0. It can't be negative, but it can't be positive because it can't be y 0. Okay, so that's quite a common trick when you need to enforce a certain condition based on a binary variable, then you do it in a way like this. And you use a number which is large enough so that it doesn't do anything when you don't want it to do anything. In this case, 200 is enough because the total is 200, so you won't spend more than 200 with any one of them. So this is what it does. Any questions about this? Questions about anything else? So what's next in the handout? What's the last thing? Okay. So we don't have to finish it. What else have to finish it? Well, this one I can't remember. That's complicated. think I've left out the resource profile for each of the projects, but it doesn't really matter. Okay. Are you ready to start this? This is complicated. I'll start not by the decision variable, but actually by summarizing what the available data are before we get to the decision variable. So we have a set of available projects. And then we have a set of months. Which is the time horizon. So, okay, we don't have the set of months, but we'll create the set of months. Oh, you can't see anything, can you? Why don't you tell me? It looks almost as if you don't want to see anything. Okay, we assume that the months are the first month, the second month, and then there are certain finite number of months that we can do the project in. And that's when we want to finish them off. And so. Okay, that's what we have. The next thing we have is we have the duration of each project. So DP for each of the projects is the duration of project P in months. And there were some resources. So this is the amount of resource used by project P in month T of its construction in month T after. Okay, so it starts, and then in the first month it uses R71, and in the second month it uses R72, project 7, and in the third month it uses R73. And then because the 7 was, for example, was 3, then after the third month it doesn't use anything, and it stops and it's completed. And then after the third month, so from month 4 on, it has benefit B7. So BP is the benefit of project P after completion. Per month. I think we'll have to finish it next week. And then there's MM, which is the amount of resource that's available in month M. I'm just testing whether students learn better when colors are used. There's a bunch of decision variables. So we're trying to decide when to start each project. Okay. So you could have a decision variable for each project, which is the number of the month when it starts. You could do, but you'd be in trouble because it would be extremely hard to do anything with it. Well, it would be complex. So instead, what you have is a trick. So it's a typical trick, in fact. So what you have is you have a 0, 1 variable for each project and month. Okay? And so for each each project in every month, you have the decision whether it's starting in that particular month or not. Does that make sense? Yeah. So you have 0, 1 variables for these things. So the decision variables are I call them SPM. I'll not ask you this time because I will get lost in my notes. So I'll just call them SPM. And there's one like that for each combination of project and month. And SPM is equal to 1 if project P starts in month M and is equal to 0 otherwise. I don't think we have the time to finish this now, so but the homework exercise. gives you two exercises. One of them is not really an exercise because it gives you Mosul code for the shift problem. And shows you how to do. So everything is the same in Mosul. Come on. Okay. Everything is the same in Mosul. You just have to put a constraint there that says that a particular decision variable is integer. Yeah? Somewhere there you find it. And the second example tells you to solve the telecoms example. And then instead of integer, which I like to say that the frequency variable is binary. It's the same as what you would like to do in the